The system we developed is called Smart Pet Care. Our aim is to enable the user to control and manage the life of his pets even when away from home. We begin our demo with a brief description of our system. It exploits MQTT and REST communication protocols. The first actor we talk about is the catalog, which provides information about the system to every other actor. It retains also information about the actors registered and active in the system. The exposed methods allow to download or upload the catalog content. There's a thread that removes actors with 2 old timestamps from the active actors list. We have 3 control strategies: Smart Toy, Smart Food, and Smart Location. The devices of those strategies are grouped in structures called boxes. Every box has its own topic and its own TeamSpeak channel. The end user interacts with the system through a Telegram bot and through FreeWord. CherryPy is used to expose the catalog through REST API. Now, we start the catalog manager inside the Raspberry. There is a configuration file that contains the address at which the catalog can be retrieved, and every actor that needs to get information from the catalog has the same address in its configuration file. Let's now start the I'm Alive manager. Every device needs to tell the catalog that is active publishing this information in the I'm Alive topic. The I'm Alive manager is a subscriber of that topic and manages the update of these devices on the active section of the catalog. Let's now start the weight. The weight is a dummy sensor that publishes the read value. In a real case scenario, it should read the output of a load cell. In our simulation, the food level is read on a JSON file. The weight checker is the program that makes the control strategy smart. It's a subscriber of the topics where weights publish and also a publisher in the actuator's topic. When the message is received, the program gets from the catalog the threshold and the ID of the actuator associated to the weight that sent the message, then confronts the value with the threshold and publishes the command on if the value is lower than the threshold. The actuator instead is a subscriber that reads the command published by the weight checker. It checks if the message is for him and activates. In reality, it may activate a mechanical devices, but in our simulation, it sends a GET request to the simulator.py program. We can see that the command on is received because the weight published a value that was under the 12 threshold. The food simulator has now started. It also has a thread that decreases of random quantity the food level after a given time interval. We can see now that the value is 0 from the weight, the command on has been sent, the food has been given, and the get request has been done. In the next message from the weight, we will see that the new value has increased. Now, there is also the possibility to activate manually the actuators through a message from the Telegram bot that we have now started. We have also started the manual actuator.py program that receives the bot request from the bot and sends an MQTT message to the actuator. We now log in the Telegram bot with our credentials that can be found in the catalog, and through the commands wait, inserting the wait ID, and then the command refill, we can send to the actuators the command on. We can see that the command has been given. We can also use the Telegram bot to change the threshold. Now let's see that the value has increased in the food. We can, now it's 39. We can change the threshold with the command thresh, the ID of the weight and the new threshold. In this case, 6. We can see in the weight checker that the threshold will now be 6 instead of 12. While the smart food control strategy is running, let's take a look at the smart toy control strategy. First, we start the peer from the Raspberry Pi. The peer is a sensor that publishes in the peer topic the presence or absence of the pet with a certain time interval. It will publish a 0 value if the pet is not present and the value 1 if the pet is instead present. The peer manager that we now will start is a subscriber of the peer topic. When the message from the peer is received, this program checks in the catalog the toys connected to the peer and publishes the command on or the command off, depending on the presence of the pet in the toy topic. Let's now start the toy. The toy is, like the actuator, a subscriber that reads the command published in the peer manager. It checks if the message is for him and activates. In reality, it should activate a mechanical device to turn the toy on, but in our simulation, it publishes on the toy command topic that is created just for the simulations. We can see that while the value is 0, the command is off, but when a hand, in this case, passes in front of the peer, the command is on, and the toy publishes the command received on in the toy command topic. Now, let's take a look at the smart location control strategy. This strategy exploits only the REST communication protocol through the Telegram bot that we have now started. Let's now start the smartlocation.py. This program checks the MAC address of the Bluetooth devices that are sending packages. For this reason, we will need to put this program inside a device with a Bluetooth module. Every pet has a Bluetooth beacon that we simulate with our smartphones, which MAC address is unique and correlated with the pet's name in the catalog. When the post request is received, the program checks in the section pets of the catalog the pets that have their MAC address on the sniffed list. We can invoke this post request through location command in the Telegram bot. We can see that now the smart location program will sniff the MAC addresses and will find none of the pets. Now let's turn on the Bluetooth of one of our smartphones that will simulate the pet present, and let's restart the location request. In this case, the MAC address found will be the one of the pet named Demone. As the user desires, he can retrieve a photo from a webcam attached to a Raspberry, where the pet can usually be found. We need two programs, one that exposes the static resource and another one that activates the image acquisition. Let's first start the photo exposer program that will be the one that exposes the photo as a static resource and will send also the I'm alive signal referred to the webcam. Then we start server photo. This program exposes a get method that triggers the webcam image acquisition. The Telegram bot does the get request to server photo and then does another one to photo exposer. The photo is then sent to the user. Let's do a demonstration. We first log in to our account, and then through the command photo and ID of the webcam, we can retrieve the photo. The ThinkSpeak adapter is a subscriber of both all weights and all peers. As we can see, both of these sensors are now active in the catalog. When message from a sensor arrives, the adapter checks in the catalog the box and the ThinkSpeak field of the sensor. Every box has its own API keys and channel ID needed to update ThinkSpeak. With this information, the program fills a JSON file where the bodies to use the bulk post request. Every 60 seconds, a thread will do all the necessary requests and then empty the file. Since ThinkSpeak channels belong to boxes, user will use Freeboard to check the information in their own boxes. The user has to log in with the credential present in the catalog and then select a box to visualize. Let's now see an example of the login in the Freeboard account. We insert the box we want to visualize, and then the HTML page will open, deploying the box content through Freeboard. This is a comparison between Freeboard and ThinkSpeak channel. For the purposes of the demo, we used very short measure time that can be adjusted in the final deployment.